In this video, we're going to recap a little bit of what you've learned so far about kinetics and reaction rates. Specifically, we're going to be thinking about what we really mean when we say reaction rate, and we're going to use a simulation to help us explain the conditions that must be met in order for the collision of two particles to result in a chemical reaction. Another word for this idea is collision theory. So this video is going to focus on reaction rate and understanding collision theory in a more visual way. Let's go. A reaction rate is the change in concentration of a reactant or product with time. A rate is always a change over time, right? The speedometer in your car that measures how fast you're going in miles per hour is giving you a rate. Now, for a chemical reaction, you're not measuring the speed in distance. Instead, you're measuring the speed in how much product is being made in a given amount of time. And the way that we measure how much product there is in science, oftentimes, is using a measurement called concentration. So we are really measuring this in a concentration unit called molarity per second. So reaction rates are often talked about in units of big M/S, molarity per second, change in concentration per second. We can look at a visual example for how we can think about that on a simulation here. So this is a PhET simulation that we're going to look at again later in the video. And let's go ahead and take a look at this reaction of particle A, which is going to crash into particle BC to react and form particle AB plus C. So I'm going to go ahead and put some particles in our reaction chamber here. And so we see the pink and purple is particle BC, the yellow is particle A. And notice that this reaction rate would be 0, right? None of the yellow particles, particle A, are forming particle AB, which is one of the products. I don't see any product particles forming there. So the reaction rate would be 0 right now. If I increase the temperature, let's see if we can begin to see. Okay, see, there is a product particle. There is another product particle. As the temperature continues to increase, you might see some more. So the rate of the reaction is the rate at which product particles are appearing in a given reaction chamber. We're going to think about the different variables that can influence the rate of reaction. We'll be looking at two different simulations during this video to help us think about chemical kinetics and reactions. We're going to start by looking at the CK12 simulation, chemical and physical changes, and specifically, we're really going to focus in on looking at the reaction that occurs when wood burns. So we'll go ahead and watch this reaction. This is a great animation that shows the particles as this combustion reaction occurs. So we can see in the wood, we have a carbon-hydrogen compound. Here's the O2 molecules that need to react. Notice that in order for this reaction to occur, here's the H2O and CO2 products. In order for that reaction to occur, the oxygen, the O2, had to collide with the hydrocarbon compound. So this hydrocarbon compound needed to break apart so that the bonds between all of the different atoms could rearrange and form CO2. We're going to watch the animation one more time. And notice in this particular simulation, it doesn't look as though it's that difficult for this reaction to happen, right? There comes the O2 molecule, it hits and there it goes. Bonds are broken, reforming, and now we have a chemical reaction that is taking place. So this simulation is a great way to visualize how bonds between atoms break and then form. But we're going to think a little bit about what conditions need to be true in order to make that reaction happen. You might notice there is a fire burning in the corner of this simulation here. That is representing lots and lots of energy. Let's think about how that energy is going to apply. We're going to switch over and look at a PhET simulation now. Before I do anything else, let's just take a moment to look around and think about what the simulation is showing us. We're going to keep it simple for now. We have a reaction here that can occur. Particle A
will react with compound BC. So particle A is by itself, it's its own chemical element. It is not bonded to anything else in a compound. BC is a compound. A single replacement reaction can occur where A ends up bonded to B and C ends up by itself. So I'm going to pump this pump here, and we'll start putting some A particles into that box, and now I'm also going to add some BC particles. So these are the particles that, according to our reaction equation, should react with the yellow particles, with the A particles, to form AB particles. But I don't really see anything happening. The particles are hitting each other, but they're not changing, right? I still see purple stuck to pink. I still see yellow by itself. So let's try and raise the temperature a little bit. I can do that over here. Raise the temperature. Notice what is happening to the particles. Think about this for a moment. What's happening to the particles when I do that? Here, I'll lower the temperature again. What is physically happening to the particles when the temperature lowers? So I just lowered it, compared to when the temperature rises. Do you see that? Do you see how the particles move faster? Temperature is a measure of kinetic energy, right, which is just the speed of particles. So let's see what happens if we can make the particles go faster. You can almost think of these like billiard balls, like pool. Oh, what? Something happened there. I see a new compound right here. I see A bonded to B. I see another one there. So increasing the temperature, increasing the speed of the particles seems to have increased how many of these particles were reacting. Let's do it again. Let's increase the temperature even more. Now, some of the particles are actually going back the other way. A and B are breaking apart, and B and C are bonding together. Again, this reaction can go in both directions. But notice how much more reactions are happening now that the temperature is high. It seems like almost every time a particle collides, as long as it's going fast enough, a bond breaks and then a new bond can form. We're going to clear the container. We're going to think about what we just noticed. So it seems as though when the particles move faster, they're more likely to result in a bond breaking, which can then allow a new bond to form, than they are when the particles are moving slower when they collide. This is why one of the key things that is necessary for two particles to react chemically when they collide with each other is enough kinetic energy, or a high enough temperature. This is one of the reasons why we cook our food at higher temperatures. Part of it is to actually change the chemical composition of our food, and part of it is just to make the whole process happen faster. We're going to take a look now at another factor that can influence whether or not we are going to see a reaction occur. So we just looked at temperature. Now we're going to look at shooting this particle. So in this reaction, right, again, we have BC, compound BC here, and I'm going to shoot particle A at it. And we're going to see if I shoot it with enough speed. That must not have been enough speed, right? Because the particle did not break apart. Let's try it again. If I shoot it with enough speed, as we just talked about, the reaction can occur when particle A hits particle BC. It'll break the bond between B and C, allowing a bond between A and B to form. So besides temperature, we can also think about the orientation or the position or the angle that the particles are colliding. So I'm going to shoot at just a random angle here. And let's watch and see what happens when the particle A collides with particle BC at a different angle.
Did you see that? Even though particle A was moving at the same speed as it had been before, I pulled the slingshot back all the way, it didn't result in a reaction when it collided with particle BC from the other side. Let's watch that again, and let's watch it compared to the time where the particles collided and resulted in a reaction. Let's watch one last time. So notice on the left-hand side, the yellow particle A collides directly with the front of the pink particle, of particle B. And the bond between B and C breaks, allowing a new bond between A and B to form. The chemical reaction has occurred. Compare that to what happened in the right-hand side, where, again, the temperature was the same, the amount of kinetic energy, the speed was the same, but the yellow atom, A, hit the other particle from above at a different angle. Instead of colliding directly head-on with the pink particle, it kind of collided with where the pink and the purple particle met, and it did not result in a reaction. This is an example of how orientation, or the positioning when the particles collide, matters as well. So it's not just about how fast you're moving, but about whether or not the particles hit each other in the right place. Let's check back in on our learning goals. Hopefully you now feel like you have a more solid introduction to the idea of reaction rates and what's really necessary for a reaction to happen when two particles collide. Remember, it takes energy to break a bond. And so when a bond needs to be broken in order for a reaction to begin, the particles that are involved in the reaction need to collide with enough kinetic energy, a high enough temperature, and be in the correct orientation, right? Be facing the right angle in relation to each other in order for the reaction to occur. We're going to be thinking about what factors we can control as chemists to influence the rate of reaction and whether or not the reaction is more likely to move in the forward direction or the reverse direction. Great job.